Hello, everyone, and welcome to APS webinars. Before we get started, I want to remind you all that if you want to hear about other APS webinars, to please sign up for our mailing list. You can sign up by visiting the URL that is visible on your screen, www.aps.org/careers/guidance/webinars. The title of today's presentation is Preparing for the Physics GRE, Strategies for Success. I'm Crystal Bailey, and I'll be your host for today's broadcast. Thank you all so much for joining us. APS webinars are brought to you as a service of the American Physical Society, connecting you with the expertise of individuals who can offer insight into physics careers, educational programs, and professional development for students, working physicists, and educators. Today's webinar is being recorded, and everyone who registered will receive a link to the recording. Please allow 24 hours for video upload. After our speaker finishes the presentation, the remainder of the program will belong to you for our question and answer session. Because of the number of people attending this webinar, we are only accepting text questions. So if you have questions during the broadcast, please ask them in the question box located on your screen, and we'll try to get to it at the end of the presentation. Lastly, we encourage you to complete the survey upon exiting, so that APS webinars can improve its ability to provide you with these valuable services. And so with that, we're going to get started. Our speaker, Yoni Khan, is a theoretical physicist whose research is focused on dark matter and supersymmetry. Currently a postdoctoral research associate at Princeton University, Dr. Khan received his PhD in 2015 from MIT under the supervision of Jesse Thaler. He holds joint degrees in music and physics from Northwestern University, and completed Part 3 of the Mathematical Tripos with distinction at the University of Cambridge in 2010, supported by a Churchill Scholarship. Dr. Khan was an NSF Graduate Fellow and recipient of the Andrew M. Lockett Memorial Fund Award for Graduate Research at MIT. In 2016, he received the American Physical Society's J.J. and Noriko Sakurai Dissertation Award in Theoretical Particle Physics. He also co-authored a popular book on GRE preparation called Conquering the Physics GRE, which is available on Amazon. And with that, Yoni, take it away.
Thanks very much, Crystal. Welcome, everyone. I'm very happy to be here. So I will talk to you about preparing for the Physics GRE and give you some strategies for success on the exam. Let's just start off by a very brief overview of what the test is. So most of you, if you start preparing, you probably know this, but it helps to just go over it to put everyone on the same page. There's 100 questions, which you get 170 minutes to answer. It's a multiple choice format, so each question will have 5 answers. And the content of the test covers both the standard and somewhat less standard aspects of undergraduate physics. So on the left column over here, you'll see the more core subjects. Classical mechanics makes up 20% of the exam. E&M makes up 18%. Optics and waves another 9%. Thermodynamics and statistical mechanics 10%, and quantum mechanics 12%. So about 70% of the test is what we consider core subjects that make up an integral part of the undergraduate curriculum. The remainder 30% of the test covers kind of a grab bag of topics which you may or may not encounter in your standard coursework. There's atomic physics, which is 10%, special relativity 6%, lab methods 6%, and specialized topics 9%. So that last one is really the most of the grab bag. It contains anything from some aspects of condensed matter physics to particle physics, or maybe some astrophysics or mathematical methods. So before I get to particular test strategies, I just wanted to ask all of you what you thought were the areas that you were most concerned about on the test. So Crystal, if you could launch the first poll. So among the core subjects, I want to know what of those 5 are you most concerned about in terms of your level of preparation, just to kind of get a sense of where the audience is.
Okay, we're going to leave it open for a few more seconds. We've got quite a few folks voting, so. Okay, we are closing the poll in 5, 4, 3, 2, 1.
Okay, so it looks like we have a pretty even split among the things that people are the most concerned about between E&M and thermodynamics and statistical mechanics, and also quantum mechanics. So it looks like most people are not so worried about classical mechanics, which is good. I mean, this makes up most of the test. So the fact that you're not worried about it means you're already off to a great start, because this is material that you learned in your first year of undergraduate, and it's pretty easy to go back and review. So the fact that quantum mechanics is up there is important because this is the most advanced of the standard undergraduate physics. But the nice thing is, if you look at really what they mean by atomic physics on the GRE test, it's really a good bit of quantum mechanics. So things like perturbation theory, if you're talking about an electron or an atomic electron in an electric or magnetic field, that counts as atomic physics for the purpose of the test or how they classify questions, but it's really quantum mechanics. So by studying quantum mechanics, you're really also getting a leg up on one of those more specialized topics also. So this is good both for you to know and then also to know what your fellow students are concerned about, and to think about how to guide your reviewing as you prepare for the test. So now I want to ask the same question among those 4 more advanced topics. So if you can launch the second poll, also same question among those atomic physics, special relativity, lab methods, and specialized topics. What are you the most concerned about?
Okay. Votes are trickling in. Okay, we're going to close the poll in 5, 4, 3, 2, 1.
Great. So it looks like the clear winner there is specialized topics. And frankly, this is what I was expecting. It's kind of hard to study for a subject where you really don't know what's being asked. The nice thing here is that these questions are really only surface level. You're only ever going to get kind of memory recall questions like, what's the name of this particle, how does it decay, what's the name of this crystal lattice, that kind of thing. So despite the fact that it actually makes up a surprisingly large amount of the test, so almost 10% is sort of a random fact recall, my recommendation for studying for these questions is really just read casually on the subjects that you're interested in. So I'll talk about resources for the test on the next slide. But really, the best way to study for this is just to pick up some books that cover the topics that you're concerned about. Particle physics, David Griffiths has a great book. Condensed matter, there's some introductory condensed matter books. And just kind of read about it and get those words in your head so that when you get to fact recall in the test, it's not so hard to just sort of pull a fact out from the back of your brain. As I mentioned, atomic physics is really mostly quantum mechanics. That's kind of covered there. Special relativity, again, most of you should probably see that in an undergraduate course, but really given that it only makes up 6% of the test, I wouldn't worry too much about it. One way to think about these specialized topics questions is they're really free points, because it's either you know it or you don't, so there's really no point in spending more than 10 or 15 seconds just asking yourself, do I know the answer to this? If not, don't worry about it. If you do, it's free points. So my advice is that despite the fact that I think a lot of you are concerned about it, it's not really that scary, and you should just treat it as an opportunity to just learn some trivia about a more advanced topic. Okay, so now let me suggest some reference materials that you might want to use in preparing for the test. So as Crystal mentioned, I co-authored a book with Adam Anderson, who's an experimental physicist at Fermi Lab, called Conquering the Physics GRE. That's available on Amazon, and what it contains is review material and practice questions for each subject area that I just discussed. There's 3 full-length practice tests with explanatory solutions. And then there's also a chapter on tips and tricks specific to the physics GRE. And actually, that's what I'm going to talk about for the remainder of the webinar, just kind of lead you through those test-taking strategies, which will remind you of other test-taking strategies for multiple choice tests, but are especially appropriate for a physics test and the physics GRE in particular. Of course, you can't do better than the material that's been released by ETS itself, since it writes the tests. So the most recent sample test that's been released is from 2008. If you go to ets.org and you search for physics GRE, it's in their practice booklet. They give you some explanations on the test breakdown and then have the practice test in exactly the format that you would see it. There are 4 previously released GRE tests floating around the web in various places. One nice website is grephysics.net. It's a very old website, about 10 years old, but what the author did is compiled all of the questions in a kind of an interactive format that lets you jump around from test to test, sorted by subject area, and see written solutions contributed by other students. So it's a really nice resource. But I do want to caution you that the most recent tests from 2001-2008 are probably the most representative of the current test. the distribution of test questions has changed a lot over time. So you'll see a lot of questions from like the 1992 test, which you almost certainly will not see today. So just be aware of that if it seems like it's kind of out of left field or a little too hard. But the most important point about the physics GRE, as opposed to some other kinds of standardized tests, is that it is a test of outside knowledge. So you have to memorize some things. You have to know some physics going into the test. You can't just figure everything out on the spot. It's not like a logic test like the LSAT would be for law school. So with that, I'm going to lead you through some tips and tricks specific to the physics GRE, show you how they could be useful for thinking about physics in general and the test in particular, and then have you solve some practice problems using those strategies along with me, and then we'll discuss the answers. So let's get started. So the first of these tips and tricks I call Derive, Don't Memorize. And by way of example, here's a problem from one of the ETS practice tests. So a satellite of mass m, little m, orbits a planet of mass big M in a circular orbit of radius capital R. And it asks you for the time required for one revolution and how it's proportional to combinations of those parameters, big M, little m, and R. So one way to solve this question is to just remember the formula for the period of a circular orbit. You might remember that, and that's great, in which case you can answer the question right away and move on. However, if you don't need to panic, because you can also get there by rederiving that formula. In fact, all you have to do is combine your knowledge of uniform circular motion, which is a much more basic topic, and Newton's law of gravity, and you can derive the formula you need. So this is the strategy, is only memorize the bare bones you need to reassemble the more advanced formulas on the spot in a couple lines of algebra. So let me show you how that works, because the advantage is that it frees up space in your brain. You don't have to memorize all the formulas, you can only memorize the ones that you can't derive and then derive the rest. So let's see how this works. So we have the satellite moving in circular orbit. So what that means is we know that something must supply a centripetal force equal in magnitude to mv squared over r. So remember, the centripetal force is not an external force, it just says it's the magnitude of the force you need to supply in order to keep the thing moving in a circle. So here, the force that's being supplied is gravity. So the planet of mass m exerts force, a gravitational force on the satellite of mass little m of magnitude g little m big M over r squared. So knowing that gravity supplies the centripetal force, I can equate centripetal force with gravitational force and solve for the velocity in terms of the other parameters. So note that little m cancels out. This happens a lot in gravitational problems. It's because F equals ma, that m that shows up in the force law is the same m that shows up in Newton's law. So those things usually end up canceling out. Okay, but we're not quite done. We've got the velocity, and we're asked for the time required for one revolution. So there we can find that by knowing that the distance the satellite travels is the circumference of that circle, 2 pi r. And if it's going at speed v, then the time or the period of the orbit is 2 pi r over v. And then plugging in the formula that I derived for v shows me that t is proportional to r to the 3 halves. So that tells me the answer is D. Of course, you could have also remembered that this problem is actually Kepler's third law in disguise. So Kepler's third law relates orbital periods of planets or orbiting bodies to the semi-major axis, but in this case it's a circle, so that's just the radius. So you could have gotten the answer to this problem in a couple different ways, but the important thing to remember is even if you didn't remember Kepler's law, even if you didn't remember the formula for a period of a circular gravitational orbit, we could rederive using more basic formulas the answers that we need. Okay, so now it's your turn to practice. So here's another problem from the same ETS 2001 test. A non-relativistic particle with a charge twice that of an electron moves through a uniform magnetic field. The field has a strength of pi over 4 Tesla and is perpendicular to the velocity of the particle. What is the particle's mass if it has a cyclotron frequency of 1600 Hertz? So in order to solve this problem, you need one number, which you don't have to memorize. It will be in the front of your test book, and I've given it to you here. It's just the magnitude of the electron's charge in coulombs. So why don't I give you about 3 or 4 minutes to solve this problem on your own. Crystal, if you could launch the ABCDE poll when you're done, pick the correct answer, and then we'll discuss. Oh, so some people said they can't see the problem. Um,
Yes, I launched it a bit too soon.
Sorry. Oh, it's okay because I think we actually have one backup poll because I'm only going to use 4 out of the 5. Why don't we do this? Can we close the poll? We'll show you the question again. I'll give you 4 minutes on the clock now, and then we'll launch the poll again. Sorry about that.
Okay.
All right, so go ahead and keep solving.
Yeah, everybody write down your answer and we'll a new poll up there. Okay. Yoni, you just let me know when you want me to go ahead and launch.
Yeah, great. I'm keeping track of the time.
Okay.
All right, got about 30 seconds left. All right, why don't we launch the poll?
Okay. Everybody just ignore the title. Okay. We're going to close the poll in 5, 4, 3, 2, 1.
All right, so there are the answers. Everybody can see the answers, right? Good.
Yeah.
So keep in mind what your answer was, and let's go through the steps to solve this problem. Then we'll see how everybody did it. Okay, so again, we've got something moving in a circle. So same formula for centripetal force. This time, what's supplying the force is the magnetic field. So once again, if you knew the formula for the radius of a cyclotron orbit or the cyclotron frequency, you could solve this problem right away. But we're going to do the same thing and derive the formula we need. So here, the force due to the magnetic field, it's actually QV cross V, but because V is perpendicular to B, so is the problem. We know that it's just QVB, but Q is 2E, twice the charge of the electron, so there's the magnitude of the magnetic force. Set those things equal, solve for the mass, which is what we want, and we get 2EBR over V. And then the last ingredient, now we're given the frequency instead of the period as we were before, but it's just the reciprocal. So before we had period is 2 pi r over V. Here now F is just V over 2 pi r. Plug that back in, and I get M is EB over pi F. So now it brings me to a very important thing, which I forgot to mention earlier. You are not allowed calculators on the GRE. Given that, they will tend to give you numbers in the problem which make your arithmetic easy. So note how B has magnitude of pi over 4 Tesla, and there's a pi in the denominator. That's so you never have to do long division by 3.14159. Likewise, you'll note that the magnitude of the electric charge is 1.6 times 10 to the something coulombs, and we have that same 1.6 times 10 to the 3 hertz. So those things just cancel, give you a power of 10, and when you plug in the numbers, you end up getting choice A. So another example of how you could either remember a formula or derive the formula you need in case you don't. One last thing to note, E was given in coulombs, B was given in Tesla. These are both SI units, so if you did your arithmetic correctly, you can be sure that the answer will end up coming out in SI units, which in this case is kilograms. You don't need an explicit conversion of Tesla in terms of coulombs or anything like that. Okay, let's go on to the next strategy, dimensional analysis. So we all know that in physics, there's 3 fundamental units that carry dimensions. There's mass, length, and time. So everything in classical mechanics can be expressed as products of powers of these units. So for example, velocity is meters per second, or length per time, length to the first power, time to the minus 1 power. Force, you know from Newton's law, F equals ma, is mass times acceleration, so m to the first power, length to the first power, time to the minus 2 power. So in E and M, you also need charge. There's a fundamental unit of charge, and then you can express things like magnetic fields, like the unit Tesla, in terms of SI units of mass, length, and time, and then also charge. And indeed, sometimes it's easier to work with composite units. So sometimes it's easier to think about energy as a unit, or the combination of units that gives you energy, rather than separating out, for example, the units of the electric permittivity, which has some crazy units, but really what you usually get is an electric potential energy. So we'll see this in action as we go through some examples. Here's the first example. So this again is from the ETS practice test from 2001. A stream of water of density rho, cross-sectional area A, and speed v strikes a wall that is perpendicular to the direction of the stream, as shown in the figure above. The water then flows sideways across the wall. The force exerted by the stream on the wall is, and then you're given a bunch of quantities. So the first thing you might think is, oh man, I better remember my fluid dynamics. But luckily, all of the answer choices have different units. And so we can use dimensional analysis to find the answer choice that has the correct units, and therefore, that's going to be the right answer. So let's see how this works. So I've got my 3 units here, rho, which is density, A is area, and V is speed. So area is obvious, that's length squared. V, as I explained a little earlier, is length per unit of time, so L times t to the minus 1. And then density is mass per unit volume, or mass times length to the minus 3 power. So I've put these things in square brackets just to make sure to emphasize that these are not actually multiplying things. The brackets is units of mass times units of length to minus 3. If you're doing the scratch work on the test and you feel confident about it, don't write the brackets. It'll take too much time to write them. So now out of these units, we want to make something with the units of force. So again, how do you remember the units of force? My mnemonic is just F equals ma. I know what units mass has. I know what units acceleration has. I just multiply the two. Mass times length times time to the minus 2. So now I want to write that F as rho to some power, a to some other power, v to some other power. So this actually just becomes an algebraic equation, or you could just stare at it. So either way, I encourage you to work this out on your own to convince you. You can check that the solution is rho to the first power, a to the first power, v to the second power. That has units of force. And lo and behold, that's one of the answer choices. Of course, dimensional analysis will never give you the coefficient in front of the answer. So if there are two choices, rho v squared a and 2 rho v squared a, there would be no way using this technique to distinguish between them. But in this case, we were actually able to knock off all of the answer choices but one, and so then therefore that must be the correct answer. So note that there's one choice in here that has g, the gravitational constant. So if it turns out that your equations have no solution, it doesn't necessarily mean you did anything wrong. It just might mean that you need more quantities with units. So there's certainly something with the units of rho g h a. It just turns out in this case you didn't need it. You didn't need to bring in any extra information. One thing I should note here, actually, this technique, dimensional analysis, is very good for eliminating answer choices. So on the GRE, like many other 5-choice standardized tests, there's a quarter-point wrong answer penalty. So if you get an answer, if you answer a question incorrectly, you get deducted a quarter point in your raw score. The reason for that is just that to ensure that guessing has an expected value of 0. It's not really to penalize you. It's just to make sure that you don't get any extra points for random guessing. Given that, it's statistically advantageous for you to guess an answer to a question if you can eliminate at least one answer choice. And dimensional analysis is often a good way to do that. Okay, so now it's your turn. Here's another question from the same ETS test. So Einstein's formula for the molar heat capacity C of solids is given above. At high temperatures, C approaches which of the following? So now, remember that in the GRE, you've got 100 questions in 170 minutes. You want to average a little under 2 minutes a question. Last time I gave you 4 minutes. This time I'll give you 3 minutes. So go ahead, and then we'll take the poll to see how you guys did at the end. All right, about 30 seconds left. All right, why don't we launch the poll?
Okay. All right, we'll close the poll in 5, 4, 3, 2, 1.
All right, there we go. So we've got kind of a bimodal distribution between A and D. So let's work through the problem and see which one ends up being right. Okay, so the first thing to note, and this is what I was talking about with composite units. H has some crazy units, but H nu has energy by Einstein's formula, like E equals H nu for the energy of a photon. Similarly, KT also has units of energy. So here, using the fact that these two things compositely, they both have units of energy, I can look at that factor H nu over KT squared and know that that thing has dimension nothing. It carries no dimensions. Similarly, in fact, I could have known that by noting that it appears in an exponential, and e to the mass doesn't make sense. What is e to the kilograms? It just doesn't make any sense. If you've got a quantity that shows up in an exponential, or a log for that matter, it had better be dimensionless. So the only thing here that carries dimensions is the prefactor up front k, because Na is Avogadro's number and it's just a number. So what I know is that C, whatever it is, has to have the same units as K. Right now, that already allows me to eliminate choices C and E, and indeed, those are the two least popular answer choices, so it looks like everybody's on the same page as to how we get that far. Unfortunately, here we're kind of stuck, because all of the remaining answers have the same units, or units of K. 0 carries whatever units you want, and so there's no way to make any further progress using dimensional analysis. So the way that we get to the right answer is either use a Taylor expansion of that term in the fraction with the exponentials, or remember that this is actually an example of the equipartition theorem, saying that at high temperatures, solids carry vibrational energy 1/2 kT for each mode. There are 3 dimensions, therefore you get that 3. And specific heat comes from taking the derivative of the energy with respect to temperature, and that's how the temperature ends up canceling. Okay, so for the people that got A, I suspect that what might have happened is you look at that fraction H nu over KT and you go, oh man, that thing definitely goes to 0 at high temperatures. But in fact, what happens is you get a corresponding factor from the denominator in that fraction when you expand the exponential that cancels it off and ends up making it independent of T. So if you chose choice A, I encourage you to go back and just check your Taylor expansion carefully. But note, there's multiple ways to solve this problem. You can remember the equipartition theorem, you can Taylor expand, or you can try to use dimensional analysis and guess. So there's lots of ways to get to the answer. Okay, one more tip for the GRE is something called limiting cases. So let me illustrate this by way of example. Here's another problem from the 2001 exam. An infinite uniformly charged sheet with surface charge density sigma cuts through a spherical Gaussian surface of radius r at distance x from its center, as shown in the figure above. And we're asked for the electric flux phi through the Gaussian surface. So there's one fact you need to remember before you can make any progress, which is you need to know Gauss's law. So that tells you that the flux through any Gaussian surface is proportional to the enclosed charge. So what's happening is this spherical surface is cutting off some amount of its infinite sheet, enclosing some charge within the sphere, and we want to know what that is. So trying to solve the problem from scratch requires lots of geometry. One easy way to eliminate answers is to send some parameter values to physically important limits. Let me show you how that works. So the first one is, what happens when x is r? Well, that means, so imagine now shifting that circle left and left and left until it is a perpendicular distance r away from the sheet. That would make the sphere tangent to the sheet, so nothing is enclosed. So if you don't enclose any charge, you must have no flux. So I know that whatever the answer is, when I plug in x equals r, the flux should vanish. That's true for the last 3 choices, but not for the first 2, which are independent of x. So right away, I can eliminate those answers. What's another physically interesting limit? This one's a little more clever. What if I take x equals minus r? So now that corresponds to moving the sphere to the right instead of to the left, but the same thing happens. It's still tangent. The flux should still vanish. This time I can get rid of choice C, because actually that's not symmetric as I take x to minus x, or r to minus r. If I plug in x equals minus r, I get something which is non-zero. Okay, I've got two choices left, so one other limit that I can take is x equals 0. In that case, I have the sphere centered on the sheet, so the sheet basically is bisecting the sphere along a diameter. That means it's cutting off a circle whose radius is big R, so I expect something like pi r squared. And indeed, that's what I see in choice D, but not choice E. So there's my answer. Of course, you can go and work out the geometry to figure out the radius of the circle that you cut off at a distance x, and plugging in the correct coefficient in Gauss's law will give you choice D. But it turns out we didn't even need to do that. All we needed to do was take these three physically interesting limits: sphere tangent to the sheet in one direction, sphere tangent in the other direction, and sphere centered on the sheet. So often, by looking at a problem and thinking physically, you can identify some interesting limits to take, which can eliminate some answers for you. All right, so now you're going to practice. This question is from the 2008 ETS practice exam. A simple pendulum of length L is suspended from the ceiling of an elevator that is accelerating upwards with constant acceleration A. For small oscillations, the period T of the pendulum is, and then you're given 5 answer choices. All right, so why don't you go ahead and answer this question. This time, let me give you 2.5 minutes, and the strategy we want to practice is using limiting cases rather than trying to solve it from scratch, but of course you're free to do whatever you find easiest. Go ahead. All right, 30 seconds to go. All right, why don't we launch the poll?
Okay. A lot of votes coming in. And we're closing the poll in 5, 4, 3, 2, 1.
All right, So, looks like two most popular answers were B and C. C is the clear winner. But based on the distribution of the answers, I'm very happy to see that it seems like people are applying limiting cases really well. C is indeed the correct answer, so let's see why. So, one obvious limit that I can take is A goes to 0. So, the contention here is that nothing funny should happen if there's no acceleration. I've just got a pendulum sitting there. In particular, nothing should blow up. The period shouldn't go to infinity or to 0 because I know that pendulums still swing even if they're not accelerating in an elevator. So right away that knocks out choices D and E. Choice E goes to infinity as A goes to 0. Choice D goes to 0. Neither of those make sense. So the second limit that you might want to take is a little more subtle. Here I want to take A equals minus G. So what does that mean physically? It means the elevator is in free fall. It means that it's just freely falling with magnitude of acceleration equal to the gravitational acceleration, which it would be if it was just falling in the Earth's gravitational field. But I know from the equivalence principle that the pendulum doesn't feel its own weight if it's freely falling. This is colloquially known as Einstein's happiest thought when he imagined himself jumping off the roof of the building and realized he wouldn't feel his own weight. So if the pendulum doesn't feel its own weight, then it doesn't know that it's supposed to swing. It's just going to hang there. And so in fact, choice C is the only one that goes to infinity. So period going to infinity means the pendulum doesn't swing. It's the only one that goes to infinity that I haven't already eliminated as A goes to minus G. So there's a way to get the right answer with some careful thinking, but basically no calculation. So that can be very useful if you feel like your algebra skills might be a little rusty, or you're worried about making a sign error, or if you've just seen so much arithmetic and algebra on the test so far that you want to kind of use a different part of your brain to maximize your effort on the test. All right, let's go on now to numbers and estimation. So as I mentioned, the GRE is a test of outside knowledge, and in addition to formulas, you need to memorize some numbers. Luckily, based on our understanding of the test, you only really need to memorize 5. So those numbers are physically important quantities, which the test makers feel are important enough that you should actually know the magnitudes of those numbers. The most important one by far is the binding energy of the hydrogen atom. So the energy it takes to remove that one electron from the one proton in the hydrogen atom. That's 13.6 eV. Probably the next most important is the mass of the electron in units of c squared, so 511 keV. They give you the electron mass in kilograms on the test, but often its mass in keV per c squared is more useful for high energy problems. Then there's 1.22, so this is the coefficient in the Rayleigh criterion for whether you can distinguish two objects that are angularly separated by some small amount. The fourth one is 2.7 Kelvin. This is the temperature of the cosmic microwave background radiation. And the last one is this 3 times 10 to the minus 3 meters times Kelvin. It's the Wien law constant, which relates the frequency or wavelength peak in the black body spectrum with the temperature. So actually, that last one has shown up on the test. Either it's been given to you or the question has been written in such a way that you don't need it. But to be safe, I would say you should just memorize these 5 numbers, but you almost certainly don't need to memorize any others because they'll be given either on the formula sheet or the exam questions themselves. So to see how numbers like this might show up, let's go to a practice question. That this one actually comes from some extra supplementary material that ETS released describing its the structure of the exam. It doesn't come from any particular practice exam. So the ratio of the nuclear radius to the atomic radius of an element near the middle of the periodic table is most nearly 10 to the minus 2, 10 to the minus 5, 10 to the minus 8, 10 to the minus 11, or 10 to the minus 14. So note that all these answer choices are very different in orders of magnitude. So a ratio of 10 to the minus 2 versus a ratio of 10 to the minus 14 is very different. So the hope is that we can zero in on the answer without doing a lot of detailed calculation. We're just going to kind of guesstimate these sizes and the relative sizes. So the way that we do that is to convert energy to length with the combination of units h bar c, which is 200 mega eV times femtometers or 200 eV times nanometers. And in fact, this will likely show up on your formula sheet at the top of the exam. This is not a number which you have to memorize because this combination of constants shows up very often. So actually what they give you, it looks like on the 2008 exam, is HC, which is 1240 EV times nanometers. The difference is a factor of 2 pi, which should not matter for order of magnitude questions. So using these constants, let's ask, what do we expect a nuclear scale to be? What do we expect atomic scales to be? So for the nuclear scale, we know that the proton has a mass of about 1 GeV per c squared. So that's another number that you might want to memorize, or you could just sort of remember that the atomic units in GeV are very similar. Its size, using that conversion factor, lets me exchange energy, so GeV or MeV for size. So 200 MeV is about 1 GeV, so that means that that corresponds to about a femtometer, which is 10 minus 15 meters. So that's a characteristic size of a nucleon, a proton. If I'm near the middle of the periodic table, maybe I have atomic number, or atomic number 50, but then I've got some neutrons in there, so maybe it's like 10 to 100 femtometers. Just guesstimating is good enough here. On the other hand, to identify the atomic scale, I need to know that the binding energy of the electron is 13.6 eV. But knowing that, I can exchange that for a distance, which is going to roughly represent the Bohr radius, so the distance the electron is from the nucleus, and that's about 10 minus 10 meters, or 0.1 nanometers, and again, I get that from that second formula conversion factor, 200 eV times nanometers. So that tells me that maybe I would expect an order of magnitude larger, so 10 to the minus 9 meters, if I had a kind of a really fuzzy electron cloud for a Z equals 50 atom. Then if I take the ratio of these guys, so 10 to 100 femtometers is 10 to the minus 14 to 10 to the minus 12 meters compared to 10 to the minus 9. Somewhere in the middle is 10 to the minus 5, and the ratio is closest to that. So here we needed to use this one number that we memorized, the 13.6 eV binding energy for the electron and hydrogen, and we also actually need to use the fact that the proton has mass of about a GeV, or that nuclear scales were close to femtometers. So that might be one extra number you might have to memorize, or you might be able to derive that if they gave you the magnitude of the proton mass on the test. Okay, so now we're going to have you practice with one last question involving one of these numbers you have to memorize. So two stars are separated by an angle of 3 times 10 minus 5 radians. We want to know the diameter of the smallest telescope that can resolve the two stars using visible light of wavelength 600 nanometers, and you're supposed to ignore any atmospheric effects. So now to give you a sense for the timing you might expect in the GRE, I'm going to give you 2 minutes. Go ahead and start. All right, 30 seconds to go. And stop. All right, let's launch the poll.
Okay. We're closing the poll in 5, 4, 3, 2, 1.
All right, so it looks like B is the clear winner. And B, that's the correct answer. So there's a couple ways you could have approached this problem. So again, noting the answer choices are very far apart, 1 millimeters to 10 meters, you could have used some physical reasoning to try to narrow down the range of answers. If you wanted to solve it exactly, the number you need to know is that 1.22, that coefficient in this Rayleigh criterion. Here, the angular separation is small, so I can use a small angle approximation, and then solve for d in terms of lambda and theta, giving me about 2.5 centimeters. Okay, so I want to make sure that I have enough time for you all to ask questions. Let me go through quickly just 2 more tips that you might find useful in studying for the GRE. So if you look at the kind of answer types you expect on a multiple choice question, they fall into a couple categories. The easier questions are things like we already saw, where the answer choices have different units, like problem 57 from the 2001 test, or the one we just did, where the answers are widely separated by orders of magnitude. You can use some physical reasoning to figure them out. Something like question 35, note that all the answers are a power of 3. So without even knowing what the question is, the question really is, you have some formula, which power of 3 is it? So what power is some quantity raised to in some formula? You really just need to know the formula, but you don't need to know the prefactor up front. Here, actually, the question is the black body formula, the Stefan-Boltzmann law of P equals sigma t to the 4th. You don't need to know the constant sigma, you need to know the t to the 4th bit. Then this thing like question 46 we've already talked about, so there are some different limiting cases, and then you can use some physical intuition to figure out what the right limiting cases are to narrow down the answer choices. So these are the easier question types. The harder ones are like the one on the left here, where all the answer choices have the same unit, but they have different numbers up front. So that really means you actually have to answer the question. You have to work it through from the beginning. And even worse is like the one on the right, question 33, where your answer choices are all just random numbers. So it means you're going to have to do some arithmetic and solve the question from the beginning. There's no real way to eliminate answer choices, except in this case, maybe if you realize that 3 times 10 meters per second is the speed of light, and maybe that seems like a little too high for a question like this, you might be able to eliminate that. But really the strategy here is to work the problem slowly and don't get distracted by the answer choices. So you might even want to cover up the answer choices on the test, work the problem ignoring them, and then see if the one that you land on lines up with one of those answer choices so you're not tempted into guessing one of the answer choices. The last tip that I have is just to practice on something which physicists know as Fermi problems, but which might be more familiar to you as XKCD's what-if series. So it's a question like, how many piano tuners are there in New York City? How many photons hit the Earth every day? Or a recent one for SKCD was, can a toaster operate in a freezer, which was basically estimating the ratio of the power of a toaster to the cooling power of a freezer. So solving problems like this require quick and dirty estimates paired with good physical intuition. This is just good physics, but it's also good practice for the GRE. So we have a review of this in Chapter 9, Section 6 of our book. There's also a wonderful essay you can find on the internet by Victor Weisskopf, Modern Physics from an Elementary Point of View, at that link there. All right, so that's all the tips and tricks that I have. So I want to open it up to your questions for at least the next 5 or 6 minutes. So Crystal, if you want to summarize some of the questions for me.
Sure, absolutely. Thanks, Yoni. That was great. Okay, and they're starting to trickle in. So the first question, you know there are these Case Western University flashcards. Are you familiar with those at all? And would you say that they're a good study tool?
So I've heard about them. I haven't studied them in detail. My recollection was that they were basically cutting up the 2001 exam onto flashcards and dividing up the questions into subject areas. I think that's a great idea. The risky part is that because ETS has only released 2 tests from recent memory that have anything to do with the actual test that's being used today, I would be tempted to save those exams for doing a full-length exam and exam conditions to practice right before the test. On the other hand, if the flashcards are practice problems that the group they're made up, I think those are great. I think you could do the same thing with the practice questions from our book. I think any way that you want to study that involves categorizing problems by different subject areas and focusing your study that way is great.
Okay, great. Okay, another question about general strategy. Does it make sense to, for example, go through and answer the ones you're really confident about and then going back, or do you recommend sort of, what broad strategy would you recommend for taking the exam?
Great question. So I think that any strategy that you would use for taking a multiple choice exam, which you've probably done throughout your entire middle school, high school, and college career, and maybe even elementary school if you were unlucky, any strategy that is useful for that is also useful for the physics GRE. So I would certainly recommend taking a first pass through the test, answering any questions you're immediately confident about, and skipping any questions that you know will be big time sinks. Then on your second pass through the test, you can focus on taking more time on the harder problems, and if you're really running out of time at the end, I would fall back on these tips and tricks that let you eliminate answer choices, and then consider whether you've eliminated enough choices to be able to guess advantageously.
Okay. I have a question about the book. Does your book cover pretty much all of the exam topics?
Yeah, so we designed our book specifically to cover exactly the topics covered by the Physics GRE and no others. So when we review undergraduate material, we try to distill it only to the amount of stuff covered on the GRE, actually at the expense of some really good physics, which is great for an undergraduate course, but is not great for the test. So we really made every effort to distill the review material to only the things you need to know for the test. So when we talk about Lagrangians and Hamiltonians and classical mechanics, we do not talk about all of the really interesting, particular solutions to the equations of motions. We just tell you how to write down a Lagrangian, what the canonical momentum is, and all that kind of stuff. So we really made an effort to do that, and so I hope that people will find it useful, and we're continually revising the book to try to make the particular kinds of questions in subject areas more tailored to what's been showing up on the actual test.
Okay. Are there any books that you would particularly recommend that would be useful for statistical mechanics or thermodynamics?
Great question. So in the prefatory material of our book, which I believe is actually available on our website, so it's physicsgreprep.com, we have a PDF which lists our preferred resources. So for thermo and StatMech, Thermal Physics and Elementary Statistical Physics by Kittel, Kittel, is pretty good. But I mean, basically at the level which you'll need, it's whatever book you use for your undergraduate course is probably going to be sufficient.
Okay. So there's kind of a general question here. And gosh, unfortunately, I think we're only going to have time for maybe one more or maybe two more. In general, would you say that when you're spending your time studying, does it make more sense to sort of go through books or to just doing practice problems? I mean, do you think, which should you spend more of your energy on?
I think doing a combination and ramping up to the test is a great idea. So you've got plenty of time now before the test in September and October. I would say that reviewing from books, making sure that you remember the physics, and then if you get our book, maybe doing some of the subject area practice problems is great. I would strongly recommend saving at least one full-length exam for the week before the test so that you can practice in exam conditions. And I might also suggest using the other one. If you pick 2008 to leave for later, use the 2001 exam as a diagnostic for yourself. So go through, take the test, categorize all the problems you got right and wrong, and then use that to focus your studying in different subject areas which you're either stronger or weaker at.
Okay.
One more question?
One more. Okay, this is a more general one. As a sophomore, would it make sense to take the GRE, or should this person wait until they're a junior?
So I would recommend waiting. Even if you've taken all of the courses that you need, that extra grab bag of topics, lab methods, specialized topics, that kind of stuff, will kind of percolate into your brain as you carry on in your physics career. And it's good to have those in hand because the other stuff you'll easily be able to review. There's not really much to be gained to take the test this early, and you have to pay money each time you take it. And so I would recommend waiting until your junior year, but of course that's up to you. Okay.
Unfortunately, I think that's all the time we have. I see a few additional questions. Some of them might actually be answered by going to the Physics GRE website, the ETS website, things about how many times can you take it, when is it offered, things like that. I do want to, there was a question whether or not the slides will be available. The page on the APS website where you registered, the slides and the video recording will be made available there. So you can check it out there. All right, so lastly, I'll just remind you all, in order to help us develop quality webinar presentations, please help us by taking a moment to complete the short survey as you exit the webinar today. Thank you all so much for joining us, and we hope that we'll see you again next time. American Physical Society, copyright 2017, all rights reserved. Bye-bye.